Hello, and welcome back to the race. We've been studying the points A, B, and C as they race around their respective tracks and enjoying some interesting mathematics in the meantime. We've been using these three assumptions of 1 minute per lap, theta increases at a uniform rate, and the units of the graph are in centimeters. Last time we noted that alpha is equal to the arctangent of 3 over 4 times tangent of theta, whereby alpha is the angle swept out by the point going around the ellipse. To determine the velocity of alpha, it is possible to express alpha as a function of theta and use basic calculus, but we're going to use a different approach. Remember that our definition is how many degrees per second are being swept out as alpha increases. We did agree that we would use only high school mathematics, so we're going to take a slightly different approach. Here's what we're going to do. If we look at B at a given point in time, we see that when theta is 31 degrees up here, that alpha is 24.26 degrees. So 1 second from now, B will have moved to BP, which could be B prime or B plus, i.e. theta will have increased by 6 degrees. But by how many degrees will alpha increase in the same time frame? Here's what we mean. When theta is equal to 31 degrees, which happens at 5.17 seconds, alpha is 24.26 degrees. 1 second later, when it is 6.17 seconds, the difference between the value of alpha at that point and the current value of alpha will be 5.2 degrees, which is 5.2 degrees per second, or 313 degrees per minute. So at this moment in time, alpha is increasing more slowly than theta, which is increasing at 360 degrees per minute. There's the whole thing. It's a little bit too fast to read, so we'll take a look at them in a few screenshots. So when at 4.33 seconds, the rate of increase is 5.02 degrees per second, slower than theta. And then we come up to 5.45 degrees per second when the seconds are at 6 seconds. And at 7.67 seconds, the speed of alpha increasing is very similar to theta at 5.99 degrees per second. Once we get past that, alpha is going even faster, which it has to do in order to catch up when they get to the y-axis. On the other side, alpha is still faster. They are about equal at 128 degrees, and then alpha begins to slow down so that theta can catch up. Once they get to the 180 degrees, they are at the same place, and alpha is moving more slowly. So that's what we have. Looking at this middle column, we have found out that the average of the ellipse is 6 degrees per second. Yes, because it does end up at the same place at the end of 360 degrees. However, the velocity of alpha is not constant. It varies as time goes on. Thanks for watching, and join us next time when we look at the linear speed of the point on the ellipse.